In the final section of this chapter, we're going to combine the two ideas of enthalpy, delta H, and entropy, delta S, and look at Gibbs free energy. Because combining these two ideas gives us a single term, Gibbs free energy, which will allow us to determine whether the reaction is spontaneous or non-spontaneous. Said another way, not all of the enthalpy is free, because there are changes in entropy, as we've discussed throughout this chapter, that are going to affect whether or not a process is spontaneous. So, delta G of the system equals delta H minus T, temperature in Kelvin, delta S, entropy. So this is the equation that we're going to focus on from here on out. So let's look at this mathematically, okay? And let's talk about spontaneity in some cases. Let's look at the four cases. So we have delta S being greater than 0 and delta S being less than 0. So increase in entropy and decrease in entropy. We also have delta H being greater than 0, endothermic, or delta H being less than 0, exothermic. And let's talk about whether or not the reaction will be spontaneous or non-spontaneous. And the first example that I'd like to look at is the case where delta S is less than 0. So we lose entropy and the reaction is endothermic, meaning delta H is greater than 0. So here we have a positive number and here we have a negative number, which will be multiplied by a negative, which will make it positive. So we have a positive plus a positive. This is never going to be negative delta G. Remember, when delta G is negative, the reaction is spontaneous. So if you have this as positive and this is negative, which then multiplied by a negative will give a positive plus a positive is going to be a non-spontaneous reaction at any temperature, which is shown here in red. And this is unfavorable, right? Because endothermic means you're taking in heat energy or condensing that heat energy, and you're decreasing the entropy, so you're making things less random. This is never going to happen spontaneously. Let's look at the opposite case of this, exothermic and increase in entropy. So delta H is a negative and delta S is a positive. This will be spontaneous under all conditions because we're going to have a negative minus something. So it's going to be even more negative and delta G will be negative. Well, here you're distributing heat energy, if you will, and you're increasing randomness, if you will, and both of these things are favorable to spontaneity, so the reaction will be spontaneous at any temperature. The next thing that we want to look at is the two intermediate cases. In this case, we have an increase in entropy, so this term is going to be positive, and when we multiply it by the negative, it's going to be negative. But we also have endothermic, which means that this is positive. Well, when is this going to be spontaneous? Well, it's going to be spontaneous at relatively high temperatures. Why? Because T delta S, if it becomes greater than delta H, the absolute value of this becomes greater than this, then you'll have a stronger negative, and overall, this will become negative. If we think of it from a practical perspective, the reason that this happens is because if we have an increase in entropy, that is going to have a more significant effect at higher temperatures because you're going to have a greater thermal distribution of those molecules, which will overall make delta G a negative value and make the process spontaneous. Let's look at the other intermediate case. The other intermediate case is where we have an exothermic reaction and a decrease in entropy. In this case, this is going to be spontaneous at low temperatures, and the reason for that mathematically is here we have a negative value And then we're going to have this as being a negative value as well. So we want this term to be as little as possible because we're going to have a negative times a negative and make this positive. So at relatively low temperatures, this will be delta G being negative. So in this case, the reason for this is that for exothermic reactions at lower temperatures, you're going to have a greater effect of the heat energy being released in the reaction at lower temperatures, favoring spontaneity, than you would at the higher temperatures. So overall, what is the take-home message of this chart? The take-home message of this chart is that you can predict spontaneity in two cases, okay? If you have a decrease in entropy and it's endothermic, it'll never be spontaneous. If you have an increase in entropy and it's exothermic, it will always be spontaneous. Then there are two intermediate cases where it depends on the temperature. And I should mention that high and low is a relative term, okay? Sometimes the high temperature might be, higher than practically could be obtained, or sometimes the low temperature would be close to absolute zero. I'm not saying that's exactly the case, but these are relative terms. There's no absolute value of high and low temperature. But if we have an increase in entropy and something is endothermic, then what we're going to have is spontaneity at high temperatures. If we have a decrease in entropy and something is exothermic, we're going to have a spontaneity at low temperatures. So let's look at an example here where we do exactly this. I'm going to switch over to the camera. It said, when could the following reactions be spontaneous, if ever? So here we have delta H is positive. Okay, so we have a positive value here, and delta S is positive, so we have a positive value here. Well, we want negative T delta S to be a bigger value than delta H to make delta G negative, because when delta G is negative, the reaction is spontaneous. When is that going to occur? That's going to occur at high temperature. All right, let's look at the next one. It would be easier if I could erase, but I can't. All right, it says delta H is negative and delta S is positive. Remember that this is delta H minus T delta S. So we have a negative minus a positive, or a negative plus a negative. This is always going to have a negative delta G, or it's always going to be spontaneous. Let's look at the next case. Delta H is a positive and delta S is a negative. We now have a plus another positive because we have a negative times a negative. So a plus minus a negative is going to be a plus plus a plus. This is never going to be spontaneous because delta G will always be a positive value. What about delta H is negative and delta S is negative? So in this case, we have a negative and a negative. In this case, the delta H being negative is favorable towards spontaneity, but the delta S being negative means we have a decrease in entropy, and that's not favorable towards spontaneity. So when is this going to happen? Well, you want to have low temperatures, relatively low temperatures, so that this term doesn't become bigger than this term. So we're going to have this occur at low temperatures. Let's look at a more practical example. It says, what are the signs on delta H, delta S, and delta G for water evaporating at room temperature? Well, when water is evaporating at room temperature, let's think about what we have going on. We have H2O as a liquid forming H2O as a gas. All right? So let's look at delta H. In this case, delta H from a liquid to a gas. Is this process endothermic or exothermic? Well, this process is going to be endothermic. If you want to turn water from a liquid into a gas, you have to add heat energy. So delta H is going to be a positive value. What about delta S? Well, we talked about this in just the previous section, or maybe 2 sections ago. We have a liquid going to a gas. This is increasing the randomness. This is more random than this. So in this case, delta S is also going to be positive. So delta H is positive, which is unfavorable towards spontaneity. Delta S is positive, which is favorable towards spontaneity. When would this occur? Well, this should occur spontaneously at high temperatures. So now the question becomes, is room temperature a high temperature? Well, I'd argue that's not the right way to approach this problem. You wouldn't be given one like this on a test, but from a practical knowledge, what do you know about delta G? Does water spontaneously evaporate at room temperature? It sure does. So delta G has to be a negative. So room temperature is a high enough temperature for this to be a spontaneous process. What we're going to look at in a little while is that there are specific conditions that allow this to be possible to have a negative delta G in this case. All right, let's look at a couple of examples where we actually do some mathematical calculations of these things instead of looking at them from a theoretical perspective. So number 1 says, calculate delta G for a reaction at 28 degrees C if delta H is 64.8 kilojoules and delta S is 184 joules per K. Is the reaction spontaneous? So delta G equals delta H minus T delta S. Let's think about what's going on before we calculate this, because maybe we'll know if it's spontaneous independent of the temperature. Well, delta H is a positive value, meaning it's endothermic, okay? So if it's endothermic, that's not favorable towards spontaneity. But delta S is a positive value, meaning that it is increasing in entropy, and that is favorable towards spontaneity. So in this case, we can't predict because one value is unfavorable and one value is favorable. What we can say is this should be spontaneous at high temperatures. The question becomes, is 28 degrees C a high enough high temperature? And unfortunately, there's no way to know without doing the math. All right, so delta G equals delta H, which is 64.8 kilojoules, minus, we have to convert this temperature to Kelvin, so we add 273 or 273.15 to it, and we get 301 K, so I can plug that in, 301 K. And then the other thing, which I mentioned before, but now it's coming up, is this is in joules and this is in kilojoules. We need to convert this to kilojoules probably, although it's not wrong to convert this one to joules. On a multiple choice test, you're usually going to find your answers in kilojoules. So I'm going to convert this one to kilojoules, which is 0.184 joules per K. All right, so I just divided by 1,000. When I do that, I find that delta G equals 9.4 kilojoules. So is the reaction spontaneous? The answer is no. How do I know that? Because this is a positive value. That should be kilojoules, not K. All right, so this is a positive value, so the reaction is not spontaneous. Now we're asked, calculate delta G for a reaction at 525 K if delta H is the same and delta S is the same. So essentially what we did is we found that 28 degrees C is not a high enough temperature to make this reaction spontaneous. Now the question becomes, is 525 C enough for this reaction to become spontaneous? So it's the same equation, delta G equals delta H minus T delta S, and delta H is still 64.8 kilojoules, minus, now the new temperature is, we have to add 273 to this one, and that comes up to 798 K. So now we have to put in 798 K and times the same 0.184 kilojoules per K. That should be kilojoules per K. All right. And when we do all that, we find that delta G equals minus 82.0 kilojoules. Now the reaction is spontaneous because now the delta G is negative. So somewhere between 28 degrees C and 525 degrees C, it went from non-spontaneous to spontaneous. Remember that because delta H is positive and delta S is positive, this reaction is spontaneous at high temperatures. The next question asks us, well, where's this tipping point? It says, considering the two questions above, at what temperature does the reaction become spontaneous? What is the temperature that's the tipping point? So again, delta G equals delta H minus T delta S. Well, the tipping point of this reaction is at 0, right? When delta G becomes a little bit less than 0, negative, the reaction becomes spontaneous. So instead of trying to pick a number a little bit less than 0, we're going to set delta G equal to 0, and then we're going to say at any temperature above this, it's spontaneous. So we put delta G as 0 equals delta H, which is 64.8 kilojoules, minus T, that's our variable, delta S, which is 0.184 kilojoules per K. All right. So in order to solve this problem, the first thing we need to do is move that delta H to the other side. So subtract 64.8 kilojoules. And what we end up with is negative, I'm just going to switch this to the other side, minus T times 0.184 kilojoules per K equals negative 64.8 kilojoules. Now divide by negative 0.184 kilojoules per K. Divide by negative 0.184 kilojoules per K. It's a little messy. That's a 4. Okay. And when I do that, I find that T equals 352 K. So at any temperature above 352 K, this reaction will become spontaneous. So in order to answer this question, what I had to do was I had to set this delta G equal to 0 because that's the tipping point, right? If it's above 0, it's not spontaneous. And if it's below 0, it's spontaneous. Note that the temperature is the opposite though. In this case, because delta H is positive and delta S is positive, it's higher temperatures that are favored, not lower than temperatures that are favored. So it's temperatures above 352 K that this reaction becomes spontaneous. All right, so before we do the next one, we'll switch back over here to the slides and we'll talk about the equation. I'm not going to spend a lot of time talking about the equation or the state function or any of this stuff because we talked about it previously with S, and we also have talked about it in the past with delta H. But it turns out that Gibbs free energy is also a state function, so it's independent of the path. Okay, and it also turns out that these Gibbs free energies can be looked up on tables. Gibbs free energies are very useful because they consider both the entropy and the enthalpy. So basically it's like everything wrapped into one value, which is helpful, which is, why it exists. So this is how we can calculate it. The same as before, we can do products minus reactants. Notice that we have the Gibbs free energy of formation, and the Gibbs free energy of formation of elements is 0, just like enthalpy, delta H. Also note that this is at standard conditions like 25 degrees C, a partial pressure of 1 atmosphere, and a concentration of 1 molar. And as I talked about with the delta S stuff in products minus reactants section, that's going to come up in a little while because it'll explain why water evaporates at room temperature, even though if you use standard state math, it looks like it will not. So let's look at a couple of examples of how we can use these products minus reactant stuff, both to find the delta G and to find the delta G at different temperatures. So in this table, we're given the delta H's, the delta G's, and the S's for hydrogen, oxygen, and water. You'll recall that in a previous section, we calculated the entropy for the water reaction. So you can look these up in tables. This is for a specific book, Appendix 2. I don't know which appendix it's in. You can Google this thing. All right. But it says, calculate delta G for the following reaction at 25 degrees C. is the reaction spontaneous? So these standard enthalpies, Gibbs free energies, and entropies are at 25 degrees C in the standard state. So we can use this reaction because it is in the standard state. We again have H2 plus O2 yields H2O. So we can do delta G naught of the reaction equals products minus reactants. Well, my product is water, and the enthalpy of the Gibbs free energy of formation of water is minus 228.6. So I'm going to do 2 times minus 228.6 kilojoules. Note that both of my reactants are elements. So it's going to be this minus 0 because the free energy of formation of elements is 0 and they're all elements. So here, the delta G naught of the reaction is equal to negative 457.2. All right, so 457.2 kilojoules. Is the reaction spontaneous? Yes, it sure is spontaneous. Whoops, you can't see that. It sure is spontaneous, and the reason I know that is because this is a negative value. Okay, hydrogen reacts explosively with oxygen, so it's not a big surprise that this is a spontaneous reaction. It's like, burning a hydrocarbon. It's the same thing. Those are spontaneous reactions. Now, what if we're asked for the same reaction, calculate delta G for the reaction at 50 degrees C and at 1050 degrees C? Is the reaction spontaneous or not spontaneous in each case? Well, it turns out that if you'd want to use something other than 25 degrees C, you actually can't use this because these Gibbs free energies of formation are in the standard state, which is 25 degrees C. But we can still use this. Delta G equals delta H minus T delta S. So we're still allowed to use this equation. So in order to do that, we need to find the S and the H of the reaction. The general idea here is that these do not have as big of a temperature effect as this one does, which is not surprising because this has temperature in the reaction. Now, whether or not they have zero temperature effect, I honestly couldn't answer that question without doing some research. But I do know that in a question like this, we're considering that the temperature effect of delta H and delta S is negligible compared to delta G. So if we calculate delta H and we calculate delta S, even though those are in the standard states, we can still plug them into this equation. So let's go ahead and do that. So first, we need to find delta S and delta H, and then we can consider it for the two different temperatures because the only difference is going to be T. Delta H and delta S will be the same. So to calculate delta S of this, we actually already did this in a previous section. The delta S naught of the reaction is going to be products minus reactants. So in this case, the product is water, so I want to do 2 times 188.8 joules per K minus 2, because there's 2 hydrogens, times minus 130.7 joules per K. And for this one, I want to add to that the 205.5 joules per K. And when I do all that math, which I have done before in the previous section, I find that the delta S naught of the reaction is equal to minus 89.3 joules per K, or minus 0.0893 kilojoules per K. Because if you remember, when we plug into this one, we're going to need kilojoules per K. Delta H is going to be more straightforward because the delta HF of the elements is 0. So basically, the delta H naught of the reaction is going to be equal to 2 waters. So 2 times the minus 241.8 kilojoules. And that is going to be equal to minus 480. no, 483.6 kilojoules. All right, so in this case, we have a large exothermic reaction, negative 483.6 kilojoules. And we have a relatively small decrease in entropy because we have 3 moles of gas forming 2 moles of gas. So this should be spontaneous at temperatures, except very, very high temperatures. So what we want to see is 50 degrees C or 1050 degrees C a high enough temperature? So let's do 50 degrees C first. So 50 degrees C is 323 K. I just add 273 to that. So delta G equals delta H minus T delta S. In this case, delta H is minus 483.6 kilojoules minus T, which is, I know, is 323 K, times delta S, which is minus 0.0893 kilojoules per K. And when I do that, I get that delta G is equal to minus 454.8 kilojoules. So this reaction, the delta G is negative, it's spontaneous. Okay, now let's see, I guess that's not high enough temperature to make it non-spontaneous. Let's see if 1050 degrees C is a high enough temperature. I again need to add 273 to that, which comes out to be 1323 K. Now plugging in, delta G equals the same delta H minus 483.6 kilojoules minus 1323 K times negative 0.0893 kilojoules per K. And when I do that, I find that delta G is equal to minus 365.5 kilojoules. All right, the reaction is still spontaneous. So 1050 degrees C is not a high enough temperature to make this reaction non-spontaneous. The reason for that is it's hugely exothermic, okay? It releases so much heat energy that hydrogen and oxygen are storing the heat energy, or their condensed heat energy, if you want to use the terminology from that video in the link in a previous slide, and this is less condensed. So therefore, this massive exothermic makes this reaction spontaneous, even at relatively high temperatures like 1050 degrees C. Now, you could certainly set delta G equal to 0 and calculate the temperature where this becomes non-spontaneous, and that will be quite a large number. So in the last section, what we want to look at is standard states. And it turns out that standard states become quite important for something like evaporating water. So if we consider the evaporation of water in the standard state, the delta G of the reaction for water liquid to water gas is 8.59 kilojoules per mole. Okay? And when we look at that, what we find is that this should be not spontaneous. Why should it be not spontaneous? Well, it should be not spontaneous because delta G is a positive number. But as we talked about earlier, the delta G for water is certainly negative because water, we know, spontaneously evaporates from, everyday life kind of stuff, not from chemistry kind of stuff. And the reason for that is that we have a problem with standard states. Standard states assumes that the pressure of the water gas is 1 atmosphere. And the pressure of water gas in our atmosphere is certainly not 1 atmosphere, right? That's the nitrogen and the oxygen and the argon. They add up to be 1 atmosphere pressure of air. If the water pressure was 1 atmosphere, that would mean there was no nitrogen or oxygen in the air, assuming the pressure, the total pressure of the air was 1 atmosphere as well. So that's certainly not the case. We can actually calculate delta G for current conditions by using the standard delta G plus RT ln Q. And you've actually seen Q before. Q is products over reactants for current conditions. These can be concentrations in molarities, or they can be pressures in atmospheres. Here we use R as 8.31 joules per mole K. The reason we use this R is because we want to add a term in joules, not a term in liter atmosphere. So we don't want to use 0.08206. And T is the temperature in Kelvin. So we'll do 2 examples with this, and that'll be it for this particular chapter. So let me switch back over here to the slides. Camera. It says, consider the evaporation of water under standard conditions. It is not spontaneous, and we talked about that because the delta G of the reaction is positive. So this assumes that the water vapor is 1 atmosphere. In reality, the pressure is much lower. On a hot, 32 degrees C and humid day, the partial pressure of water is about 0.0235 atmospheres. Will the water spontaneously evaporate? Well, as we talked about, delta G equals delta G naught plus RT ln Q. All right. So R is a constant, 8.31 joules per mole K. The temperature we could calculate, 32 plus 273, which is 305 K. But what about Q? Well, Q equals products over reactants. If we look here, it's going to be the pressure of water to the 1, right, because there's 1, divided by, this is a liquid. So just like in a K expression, we don't put anything that's not aqueous or gas. In a Q expression, we also don't put that. So it's either over 1 or Q simply equals the pressure of H2O, because there's only a product in the expression. There's no reactant in the expression. So here, delta G equals the delta G naught, which we have found from the original reaction, which we could put in as 8,590 joules per mole, plus R, 8.3 or 8.314, okay, joules per mole K. Note that 8.31 is 3 sig figs, 8.314 is 4 sig figs, times the temperature, 305 K, times the ln of the current conditions, ln of Q, where Q is the pressure of water, which is 0.0235 atmospheres. All right. And when we do all that math, we find that delta G equals 898590 joules per mole plus negative 9510 joules per mole. And when we add those two things together, we find that delta G equals minus 920 joules per mole. This is now negative, which explains that water evaporates under actual conditions where the partial pressure is this, nowhere near 1 atmosphere. Let's look at one more example. It says, consider the following reaction at 25 degrees C. If the pressure of hydrogen is 1 atmosphere, the pressure of oxygen is 1.14 atmosphere, and the pressure of water is 2.45 atmosphere, is the reaction spontaneous in the forward direction? All right, so now we're thinking about this in terms of an equilibrium reaction, and we want to see if this thing is spontaneous going in the forward direction. Note that we have a large excess of water. So we looked at this reaction at different temperatures a little while ago, and we found that even at 1050 degrees C, we could still make water. Well, what if we have relatively little hydrogen and oxygen and lots of water? Can we still push this in the forward direction? Well, if we remember from the previous examples, the delta G of this reaction was minus 457.2 kilojoules. Because the hydrogen and oxygen are both zero, we're basically just 2 water, so 2 times this, which is minus 457.2 kilojoules. This is in the standard state. But in this case, we want the current conditions. So the delta G in the current conditions equals the delta G in the standard state, right? Plus RT ln Q. In this case, Q is equal to products over reactants. So in this case, it's going to be the pressure of water squared divided by the pressure of hydrogen squared times the pressure of oxygen squared. So instead of concentrations, we're given them in units of pressure, atmospheres, so we can plug them in this way. So Q is equal to the pressure of, this should be water, the pressure of water squared on the top, and the pressure of water is 2.45 squared, divided by the pressure of hydrogen, which is given here as 0.100 squared, times the pressure of oxygen, which is 0.140. And when I do all that math, I find that Q is equal to 4.29 times 10 to the third. All right. So now I can plug this in, but there's one problem. My R is going to be in joules, and my delta G is going to be in kilojoules. So I need to convert one or the other. So here, delta G equals negative 457.2 kilojoules plus R, I'm going to convert this into kilojoules, 0.008341 kilojoules per K, times the temperature, still 25 degrees C, so 298 K, times the ln, I'm running out of space here, so I'm going to do one of these, of 4.29 times 10 to the third. So I'm basically plugging that in for the ln. When I do that, I find that delta G is equal to negative 437 kilojoules. So even when the pressure of water is much, much higher, right? Somewhere around, 25 times higher than the pressure of hydrogen and oxygen, the reaction is still spontaneous to form more water. Again, this has to do with, just like the temperature effect, this is a massively exothermic reaction. The delta H is very negative, a very large negative number. So that's what's driving this reaction towards forming as much water as possible spontaneously. So this has been a little bit of a look at Gibbs free energy. I think that it's really important to remember that Gibbs free energy is useful because it considers both enthalpy and entropy. In this chapter, we spent most of the time talking about entropy because we talked about enthalpy way back in a much earlier chapter that's presented in General Chemistry 1. It's a bit of a shame that these two chapters are separated by so much space, but I hope this gives you some idea of the utility of Gibbs free energy for determining the spontaneity of a reaction.